we are going to take the overview about the Neplan, then general examples, tutorials, Neplan desktop, then overview of 360 cloud-based, then some of the case studies we will go through. Then the last one, which is a demonstration that will be done by my director, Mr. Durgeshan Naikar. And the last end of the presentation, there will be a Q&A session. So the Neplan, the background and the mission of this Neplan, this is founded since 1988. So development of Neplan and power system for the power system studies, consulting, and the development of user-specific application like interfaces, database, intranet applications. Also the professional supports for the data migration and integration, as well the training on Neplan and electrical power system. So the operational main areas are Europe, America, Africa, India, and we are iEngineering are the authorized distributor in Australia. So now the Neplan Consulting Group. So what it does? So Neplan does the power system analysis software like a consulting, training of the software, as well as the consulting, which includes the planning, analysis, expertise, and services for electrical power systems. Then here we can see the versions of Neplan. There are two versions. First one, which is the desktop version. So here we can see the desktop version, which we can install in our desktop, in our PC, laptop, tablet, as well as the next one, which is the browser-based Neplan 360 version, which is a GIS-based version. So we are mainly focused on this Neplan 360 version in next slide. So this is the Neplan workflow. So Neplan for the design, operation, maintenance, as well as the research, that is the extended area. So by this workflow, you can get the actual workflow for the Neplan software, like here, the customer drawings, then the design will be done over here, then the build of that design, then the operation will be done, and last one, which is the maintenance or maintain the software. So here are a few packages, electric packages, we can say. The base modules, as well as the Neplan toolbox for the research, distribution modules, and transmission modules. So out of that, some few base modules we will see in next slides, as well as please note here is the Neplan toolbox for the research that mainly used for the university purpose. So here you can see all the packages as well as the MATLAB Simulink integrations are there. So we can use for the university. So the main characteristics for the desktop version. So worldwide in 100 countries, there are 4500 licenses, several TSO and DSO in Europe. And it's a desktop-oriented single-user application running under the Microsoft Windows XP Vista and 7.8, as we are aware about these operating systems. As well, this is a user-friendly, multi-language man-machine interface with the multi-document, multi-window systems are there. As well, compatible with MS Office packages. It's a most of comprehensive calculation and simulation tool is available. Which use of the one common database, as well the network data management through SQL database as login logout, which is possible, and in integration interface through programming library, which is also available with this software. So now the main characteristics for this web version 360, which is a fully browser-based power system analysis tool on the market. So for this, no installation needed. It's a user needs only the browser to run this through intranet or internet. So here it's a highly flexible with a new license model to meet every customer requirement. Also, it's a use of one common database, multi-user SQL database, as I said earlier. So the functionality is the same as in the desktop version. And this 360 integrates the power of GIS software, and wide range of the maps and geographical data can be used directly along with the network calculation. So this flexibility goes beyond the easiness of the browser base, since the calculation algorithms can be called directly by any external GIS, SCADA, and smart grid application. You guys might aware about this SCADA and smart grid application. So the next, which is the browser-based solution, here we can see the maps which are integrated part of the single line diagram. How we can do the data entry. So this is a well-organized input dialogues. Here you can see the parameters, where this is a tree of this dialog for the two winding transformer, and the data tables. Here we can see where the coloring of parameters has been done for the certain calculation we can do with this option. So user defined data. So as we know, for every product, there is a defined data. So here we can see the for this company, Siemens company, the user parameter data here we can put. So whatever it may be the nameplate, on the nameplate, the data which is defined here we can put. There is an option with this Neplan 360. Then the network coloring, as I said earlier, for the network coloring, all the voltage levels, phases, feeders, overloaded elements, nodes with the voltage, then supplied network. For everything, we can color the network with different color. So the whatever may be the ranges, color ranges, which is depends on the calculation results. So like a calculation for the power system studies, we are considering over there. Then next one, which is the area, zone, and substation concept. So here we can group this in a parts of the network. So data calculation from the SQL database, we have to take it. Then the coloring according to the area, zones, and substation. So load flow within the area zone control, that can be a possible, as well the results in terms of the losses, total load, total generation for each area and zones which are possible. So scaling factor for the different zones also we can define. Then next one, which is the feeder concept. So in that case, just overlook this diagrams, like coloring according to the distribution feeder. So here the automatically change of the separation point. So this is a there are two color coding for the feeder, one green and yellow or orange. We can orange we can say. So here the change of the separation point. So change of the separation point can be done easily with this software. So the result visualization, what we get from this. So the display of calculation result in single line diagram. So here you can see the single line diagram, the result tables and graphical charts and flow animation. So we can visualize all the necessary data, whatever may be the parameters which we have already fed in software. So we can see the result. So in pie charts also we can see the result, and we can analyze our power system studies. Then result visualization in GIS. So just please note, the GIS, it's not a this is a geometry geographical interfacing systems. It's not a GIS substation. So please note. So multi diagrams and graphic layers are available. So here this is a geographical representation with map background. So according to the map diagram, as I said, we are using and we are interfacing with the GIS system with this software. So the schematic diagram here we can see. So schematic representation is there with using Neplan software. So variant management system. So this management system is segregated like a base network. So it is divided in various management systems, like a variant management systems are there, but there would be a one base network. So which is the basic one. So we have to follow. So in element libraries, It can be created for all element types like a customized and the huge number of predefined element types and overcurrent protection relay types. So within this Neplan, whatever may be the network data which is updated in change library data, we can export, import with this SQL database. So there is a provision in library. Then the unique functionality or highlights we can state here, like this is a desktop browser-based solution with client-server architecture, most complete power system analysis too, very user-friendly. It's a graphical database editor with map integration, like it's nothing but the GIS. Then the protection devices fully integrated. So excellent risk-based planning tool, for example, reliability analysis, which can be done. The outstanding dynamic analysis module, the Neplan simulator is there, and the asset management tool, the open system with many interfaces, and the user modeling, and the web services to integrate with GIS and others. So now this is the one type of the project or case study we can say. So in that case, the Ministry of Power Government India has launched the Restructured Accelerated Power Development and Repose Program. So APDRP in July 2008. So with a focus on establishment of the baseline data fixation and accountability, the reduction of this ATNC, accredited transmission and commissioning losses, which is up to a 50% level through the strengthening and upgradation of sub-transmission and distribution network of this IT during this 11th plan, which provides the Neplan 360 cloud base for two regions. That regions have defined here, region Karnataka and region JNK. So for this project, we have used the GIS S3 solution. So that S3 is one type of the company who is providing the geographical software and the information system for the mapping this Neplan software. So just please note here, this is the one project which is based on this Neplan. So Neplan 360 browser-based solution. So here, how we have done for this APDRP project. So HTLT feasibility study would be there, and here the MDA, that is a master data management system, the structure you can see over there. So GIS, which is a web services to the Neplan 360 calculation and load estimator has been done within the software. Then this WM, that is a wide area monitoring. So wide area monitoring monitors the data to this Neplan library. Up till now, as we have seen the libraries also, and ultimately the final result we get after this measurement, web services and investment of data, we get the final XML result file as well as the reporting. Here we can see. So this is the feasibility. This just overlook the feasibility report for this 11 kV feeder of sub area. So from this report, we can get the losses as well as the annual energy losses. Then what would be the payback period? So we get from this report. Then next one, which is the energy loss calculation. So for the energy loss calculation, as you guys are aware about the losses, so the HT losses, LT losses, then the load loss factors. So everything we can get with this XML file, as I have shown in earlier slide. So next, which is the network. So network we can define as a feeder wise and substation wise, and the time, that means the whatever may be the losses and your payback period, accordingly we can define it in day wise, month wise or year wise. Then next one, which is mainly base modules like a load flow analysis. So in that case, the name itself indicates, as this is a power system analysis software. So for this load flow analysis, the iteration methods. So for load flow analysis, the iteration methods, you might know about this Newton-Raphson method, and to calculate this voltage drops and all these mathematical calculation. So the any combination of this 3-phase, 2-phase, single-phase AC-DC network, AC-DC converter. For example, this is the single wire earth return, SWER. So in that case, the measurement data which can be input where the load estimation is done and the load allocation within the software. So here the transformer regulation with on-load tap changer, which is available for this load flow analysis, as well the thyristor based regulator for low voltage network, then power control through phase shifting transformer like a FACS devices and HVDC system, and the consideration of the generator limits, zone area control. So all these parameters or all these necessary things we have to know for making this load flow analysis for any substation. As well, for the renewable energy sources, the models are available. You are aware about this renewable energy sources also, like a solar, wind, biomass. So the optimal power flow also done in load flow analysis. So here the example of this renewable energy source. So here we can see the single line diagram. So we can draw such diagrams in Neplan 360, our software. As well, we can put the parameters. So here the photovoltaic, we have taken the example, and the respective their parameters like active power, reactive power, power factor, current. So everything here we have defined, mainly the voltage level. And here for this single line diagram, we have done the calculation and we get the output in terms of the graph. Here we can see the graph for the modeling of the inverter control, which is needed over there. So for the smart grid application, here we need the models like a PWM, pulse width modulation converter, DC photovoltaic, DC battery, DC fuel cell, DC flywheel, and AC flywheel. So all these things you might aware, and some parameters we should know, then we can get the output result. So next study is like a arc flash calculation. So according to the standards, so there are the few more standards. Out of that, IEEE standards here we have adopted. So for the short circuit parameter calculation, so in that dialog box, standard IEEE standards, according to the requirement we can choose with this software, and once we apply the standard, so according to the parameter would be the change, and the whatever may be the single line diagram where we can get the parameters and we can get the results. That is the flow of this software. Then next, which is the overcurrent protection. You might know about the various types of the protection. Out of that, the overcurrent protection. So here you can see the bus system, a single line diagram of the bus system, where the selectivity chart here we can show, as well the relay setting. So relay and tripping time. So protection is nothing but it's related to the relay and circuit breaker, as you know. So the signal from the relay which trip, and then the circuit breaker which is the combination and the operation between the relay and circuit breaker has which is done, and we can set the delay time and respective delay time and settings we can do over there. And the short circuit analysis. So for this short circuit analysis, the methods we used, like standards, according to the standards, we adopted the methods. So for that matter, superposition method, then the 3-2 single phase networks or the single wire earth return from the load flow, as well the short circuit types. So on nodes and lines. So some standards as well as the spatial faults condition here we can consider. Then the last one, which is the current, the maximum and minimum limit of the current we have to show and we have to put. So according to that, there are various types of the current, as we know, the thermal, then the breaking current, steady state current, the peak current, so asymmetrical braking. So all the calculation of currents that has been done in software, and there is a provision to put all these things and we can get as per our requirement. So the static converter contribution to short circuit current also, which is a possible. So that is a best feature which is available for the protection purpose. Now the next one, which is a motor starting. So here we can see the single line diagram as well as the output result in chart tables for this single line diagram. So I will explain this with this next slide. As here the worst case we have shown for the voltage drop at a time t which is equal to 0. So here you can see that time and the voltage graph. So this is actually the model for the motor starting quasi-stationary model, we can say. So here we can integrate of the motion equation. So with different mathematical standard expression, we can derive the for the motor starting integration, and over there the load flow approach, then voltage drop calculation at time t equal to 0. So in the previous slides, we have shown the worst case when that time t equal to 0, and the simulation of the motor startup means at the time of the starting in any size of the network. So here we have defined for that matter, as we know, we can use for the soft starter for the startup the devices. You guys might know about this all different types of starters like direct online starters, then motor starters, rotor starters. So out of that, the soft starters here we have used. Then the next module, which is the Neplan simulator, which is used for the mainly transient stability. So model with the differential equation, subtransient model, then flexible simulation through definition of events, for example, power transfer, and the user-defined model for the motor drives through symmetrical MATLAB Simulink definition. So from this, we can get the user-defined models. Then next one, one more modules, which is a harmonic analysis. So harmonic, which is related with the frequency. So calculation types like harmonic load flow, then harmonic label, we can define the calculate total harmonic distortion, fault current, fault time, then the K factor, you might know about all these parameters. Then frequency scanning for the impedance, current and voltage source. So for this harmonic analysis, we need to know the network type, then the sources of harmonics like current sources, voltage sources, then the elements that as I said, the harmonic, which is a dependence of this frequency. So for each element can be defined as an exponential function or whatever maybe the elements defined in a table. So we can calculate the total harmonics distortion. So here I can show with more details the harmonic analysis level, TSD, TSDI, TIF, IT. Here in a single line diagram, you can see the total harmonics THD in percentage. So total percentage of this THD and respective their frequency scanning as well voltage levels. So by using this graph, we can show what would be the frequency ranges and voltage levels according to this job or this project, we can say. Then next one, which is a flicker. So in that case, the flicker where the power changes. So how it will happen? So the power changes, there are three types of power, as you know, the active, reactive, apparent power. So accordingly, the how that flicker affect on the power quality. So in that case, according to this power quality issue, we need to consider this flicker. So in that case, we can show the power changes over there and what are maybe the current changes and how it is controlled. That means power, how can we control? So respective emission limit curve we can show here as a result. So some few studies we have already done. So I request my director, Mr. Durgeshan Naikar, to demonstrate more detail with actual software to students. Thank you.
Thank you, Madhuri. Can you hear me?
Yes, yes, sir. We
Okay,
can
good.
hear you.
All right. Thank you for your presentation. I'll straight away jump into sharing my screen. Okay, you can see my screen, right?
Yes, sir. Yes, sir. We can see, sir.
Okay, so before I start, I must say that Neplan is a very, very powerful power system analysis tool. The word Neplan actually comes from network and planning. Okay, so the two words put together became Neplan. And it is very, very strongly used in India, also with a lot of, all over the world. Very powerful software, very well known in European market. And lots and lots of universities are using it for their educational purpose, okay? Where students are doing research, PhD, whatever, and they use Neplan because Neplan can very easily integrate with your Simulink and all sorts of models that you create. It can be imported and used together in power system. Okay? Now, in very simple summary, I say Neplan, it is one of the, I think from my understanding, it's the only software so far, and is the first software which has gone into browser-based approach. In other words, you can do the calculation from your iPad or tablet or any machine, wherever you sit. You can sit in a coffee shop and start doing your calculation from there. In other words, the calculation is not done in your computer. It can be done on the cloud. Okay, so we call it Neplan 360, and currently I have opened Neplan 360, which is not running in my machine. It's basically looks like a browser, and actually it's not a browser, but it is an app which sort of runs if you have the app in any of the machines to do calculations. All you do is log in and start opening your project and start using it. Neplan also, I must say, had a desktop version which is now discontinued about 3 years ago, which was supposed to be loaded in a PC. Okay, and then you all have individual versions of Neplan projects pretty much running in your computer. With this concept, we have got here the browser-based, where Neplan is the first in the world to do this. It can pretty much multiple engineers can work simultaneously on the network, on the same network. And that's the very important thing in which a lot of utilities, power utilities, they have problem. When they finish a job, they can't put it together easily. Okay, here you can do that. Now, the other thing about Neplan is one software does everything. It covers, like what Madhuri has said today, it does all the industrial type power system calculations. It does distribution. It also does transmission and generation. So pretty much it covers all the sector. Then it also does IC calculations and DC also. And it also covers very low voltage to very, very extra high voltage calculation. It can do single wire 810, as Madhuri said, and it can do 4-wire system. So pretty much one software can do everything at one place. You will notice that a lot of utilities, a lot of companies, they use 4 different types of software to do power system analysis. When you come to Neplan, you come to one shop. Basically, you get everything. Okay. So what I'll do today here, I'll show you Neplan 360 because this is the way forward. Okay. This is the latest software which is running on cloud 360. You as a student can also get a student version of it by going to Neplan 360 website, and you can pretty much use it as a student. I understand it is free for students, okay? And for universities, they can also buy the software, 20, 30, 50 nodes, and students can use it on premises also if you set it up like that. Now, here I can show you how you can do and learn a little bit from projects. So if you create a membership on Neplan 360 and then you log in, so when you go open, right, it's like any other software you use, Windows software. And under examples, what we do, we give to our clients, to our students, all these examples here. So if you want to learn about steady state, there's so many examples here. These are not just an example, they are real case study examples, okay? And there are many, many examples which you can look at and start reading what they do and how they do it, or how it's done. Arc flash, there's few here, cable sizing, and so forth, okay? There's motor starting, everything that you can think about under steady state. And then there's asymmetrical steady state. Remember, when you see these examples, they are pretty much an example from some textbooks. If you read some textbooks, they will talk about IEEE 1.2, this example, and you go and look at that example, the calculation that was done probably 30 years ago, maybe 50 years ago. The answers you get here is exactly equal to what they calculated. So what it means that Neplan does give you the right answer. Here is some DC steady state examples, dynamic simulations, and so forth. Map integration type of here, protection studies, distance protection, all sorts of overcurrent protection, all these things are there. Okay, and some examples of renewable energy type examples. Anyway, so I will not open any of them, but I'll just say, look, what I did here, I've opened a couple of examples that I sort of will run through and show you what we can do. Here in the first example, I want to show you, in this example, what we'll pretty much study is load flow and short circuit calculations. Okay, so as I zoom in into the network, I can see here's the grid which is feeding in, okay, and into this bus bar. Now you will notice that, as Madhuri said, the way Neplan works very nicely is the color. They color the bus bars pretty much in different colors. So if they are same voltage, they will be same color. You can see this is a different voltage color, so it's a different voltage. You can see it's 8.5 volts kV here, whereas this one is 65 kV. Okay, so as the single line diagram, you can see drawn here. Down here we got transformer, which is stepping it down further, and then we got some motors here, which is connected to this transformer, and there's another bus bar. So how does Neplan work? Neplan software pretty much works on number of nodes. Some software, they count number of device connection points, but Neplan doesn't work like that. Neplan looks at number of nodes. So in this case, if I look at it, I can pretty much count. It's not a very big network, and I think it's almost 13 or something. So if I don't know, I can also go on the side here and go to the nodes, and I can see there are all the nodes which is available here. Okay, so there are about 13 nodes here at the moment in this particular diagram. So Neplan also very smartly does, if you're drawing a big network, how do you manage them in one page? Okay, if I click there, it brings it to one page quickly, and then I can zoom in anywhere if I want. But what about, there's a lot more to draw? Okay, so in this case example here, can you see there's a box here? What does this box say? That if you want to go and see detail about low voltage transformer here, it's drawn not here but somewhere else, but electrically they are connected. Okay, this bus bar is connected to this transformer. Okay, a copy of this bus bar is in another diagram basically. Okay, and if I go on the diagrams here, you can see that's the first diagram where we are, the dot is there, and that's the LV diagram which is sitting behind it. So you are able to easily manage very complicated network, because your first diagram could be very nice and very simple with few things, and then as you go through different areas, you can sort of put them in different diagram. And what does that mean? You can print it out and make a very nice report in an I4 paper even, so you don't have to make a huge network and you can't organize it properly. Okay, because here you can keep connecting into diagrams after diagrams. Okay, layers after layers. Okay. Now, to go to the next diagram, all I do is basically go in here and right click here, and I say, please take me to the other graphic, which is the LV, low voltage graphic. And now the system has opened on the right side here. Can you see? It has opened me the same, for the same one, it has opened me the LV. Right? Now, this project and this project here, pretty much they are same project, but they are in different diagrams. Okay? It's one project, remember. Now what I'm going to do is try and do some calculation. And as you know, there are various modules which Madhuri showed on that PowerPoint presentation. And remember, I was telling you, you can see all the distribution, generation, and transmission, all different types of modules are there. But we will select load flow here, because we will first do a load flow study here and see how we can work through. It is very, very easy to draw this, okay, because all the tools are here and all the library symbols are on the right side. All you do is grab them and drop it in there, okay, and you can select basically the size of the transformers or whatever you're going to be using from library. If not, just for your study purpose, but if you really have the actual data of from the nameplate, you can insert or fill in those data. Okay. For example, here currently I'm looking at a transformer, and if I double click on this, I go and I've given a name here. It's a 3-phase transformer, and actually the size is 200 MVA. Okay, and it's telling me the primary voltage is 220 kV, and the secondary is 65 kV. Okay, so basically you know what is the turns ratio, right? And it's got an on-load tap changer. Okay, and if you go to the regulation section, and you can see it's basically it's got all the taps, and it can automatically change its tap as the voltage as the load increases to maintain the voltage to the requirement. So it's normally the bigger transformers will be always on load tap changes because they want to regulate it automatically. Down below where you have a like a distribution transformers, LV transformers, let's say, low voltage ones, they are normally not automatic or on load tap changes, I think. Okay, so let's do the calculation. Before I do that, just to point you out, there's also a generator sitting in our network, and it is connected through a transformer into this bus bar. Okay, so everything there, whatever you can think of, you can draw it here. Okay, and then if I hit this calculator here, it will start doing the calculation. But before I need to set some parameters. Now, I remember Madhuri talking about the method we're going to use to calculate. So we are using extended Newton-Raphson method. Okay, you can use current iteration, and you can use various others. Okay, so it's up to you which one is you've been asked to do and calculate the answer. Few methods are available there. Okay, it also tells when should we stop after 20 iteration, and if the answer doesn't match within 0.001, of what's required in 20 iteration, please stop calculation, and it will bring up an alarm or a message saying it's not done. Okay, various things can be set here. Voltage levels, this is important. Remember, I told you the colors. You set the voltage level and you tell what is your minimum voltage you want. Okay, and maximum at this particular nodes. I can dial in any number here. I can make it 97, 95 here. Okay, I can change it if I want. But I want my study to be done at 95 because that's what my client wants. My client doesn't want anything, none of the nodes to go below 97% of the rated voltage. Okay, nominal voltage, I mean. So now, okay, I do my calculation. Okay, calculation done, finished. The results are on the board. Okay, and you can see what's happening from here. How much power is coming in or out? Well, currently it looks like power is going back. Can you see? Can you see this arrow going left back? It's going up. So, but whatever, because this generator is producing power, okay? Power is going down. The arrow, can you see here maybe? And then it's going up all the way through this. Now, but can you see here? Obviously, we have a load, right? We have got some load here, and in the other page, we have got a load here. So, but we see a problem here. Neplan will start flashing. Will start flashing yellow color and say something is wrong here. So what we can see is the voltage we are getting is 95. Okay. And remember, I showed you in the table that it is 97. And because it's below 97, it's complaining at node number 10. Now, let's say, just to show you that if I go back to my voltage level and I go to, what is node 10? So this is actually 4.5 volts here. So if I go here, and if I change the setting, okay? And instead of that, I say make this 95, because I know I'm getting more than 95. So I'll put 95 just to show you that Neplan will be happy, because we have said at this voltage level, okay, the gray one, we're going to be considering 95. And this should say I'm happy now. Okay. So now nothing flashes because our reading here is above 95. Of course, it's above here 95. So no issues. Okay. But that's not what we should do, right? We should fix the problem. So we'll go back and put our levels back to 97 as we had before. And okay it. And obviously now if I do, I get a problem. So what then happens here? What can we do about it? Well, there's two things we can do to fix it. One is we can reduce our load, okay? Or secondly, if I can go and change my tap setting here. So the easiest thing is probably, I mean, obviously you can't reduce the load here because you may need it, but I'll show you we can do it that way. In between the transformer to this, there is no cable at the moment in this particular project. Sometimes you could increase the cable size to reduce your voltage drops, okay? But here it's not, actually it's directly connected to the transformer. There is no cable run, okay, in this particular part here. But to show you one method to solve it, let's go to the regulation and we will put the actual tap just one up. And by moving one up, it's telling me it's going to increase the voltage by 2.5%. Okay. So I'll go okay. And I'm now going to run it, and I hope I fix the problem. So as an engineer, you can tell the people out there that when you're doing this one, make sure you put your tap at 1 for this transformer so that you don't get a voltage drop issue here. So you can see you have simulated it, and you found that you are getting 97 here. Okay. And that is good enough for you, probably. If you go to tap, next step, it might be even more. Okay, it might go to, where is it here? And it will increase to probably 100% because we are putting too much now. And that is also fine. You know, it's getting the full voltage. So calculation is done now. Okay. And you can see the voltage is 100%. There's no, whatever is required is actually 5.2, and that's what it is here. All right, so that's one way to give it a quick fix. Or, like I said, let's put it back to 0 tap setting. And then we go into our transformer, in the motor. And as you know, this motor is 5 megawatts. I will try and reduce its actual power here. So it says it's running a 4. I'll make it 2 and make this 1. 4 and 3 became 1, just to reduce the load, okay? And that should fix the problem. So what I've done instead, I have reduced my load. So if you reduce the load, voltage drop will go away. Okay, so can you see it's now 98.5%, which is fine and no complaints. Okay, so I'll put it back to where it was. Right, so that was about pretty much load flow. And if you want to get the result, you can go into this place here on the table, and all the results can be shown, and it can be exported in an Excel format, and you can do whatever you want with it after that. Every different readings can be coming from here. Okay, so the results can be shown on the graph like that. Okay, and it can also be put in the table. Now, if I go back to next calculation, let's say short circuit. So I just change here on the top the module. And before you do short circuit study, you need to have a place where you have created a short circuit. Okay, otherwise it's not going to do any calculations. I'm going around, but there's no short circuit. Now, by default, there are some short circuit points here. How do you know where they are? I can know by going here on the table, and I say, let me look at if there's any short circuit on the nodes. And I can see there's a dot here. I don't know whether you can see. Node number 12 has got a short circuit. Okay, if I untick this, then there is no short circuit there. Okay, is there any short circuit in a line? Now, obviously, you don't have short circuit only on the bus bars or nodes. You can also have it in a cable. In other words, there's a cable and probably 20% from the start, or whether you want to say in percent or meters away from the area, there's a short circuit. So here you can see line 5 and 6 over here. We said there's a short circuit at 50%, which means right in halfway point, whatever the length of the cable is, half of that there's a short circuit at the halfway point. It could be 3/4. It doesn't matter. In this particular example, we got 50%. Okay, so what you want to know? If you want to know what will be the fault level if the short circuit happens 50% on the way in the cable, halfway on the cable, what will be the value? And that's one more thing. Okay, so in that case, we are ready to do that. Let's run the calculation. But before that, another thing is what type of fault you are doing is also important. Currently, we are looking at 3-phase fault. Okay, you can find phase to ground fault. Okay, very important study is this one, especially for earthing design and studies. Okay, we can have 2-phase. We can do 2-phase to ground also. We can do special fault. What is special fault? Now, a lot of substations don't have this special fault. What does special fault means? Well, it means you could have a 132 kVA line running on a same pole, shared pole, with a let's say 11 kV line. And what if that falls onto a 11 kV? What will happen? Now, Neplan can also study those sort of things from one voltage level to another voltage level, not only to ground or not within itself. So it's quite an amazing tool. Okay, so there are various things it can do. So I will just do a 3-phase study. Doesn't make difference in pressing the button to do the other ones, but we'll just do one study. And of course, there are various standards that are required. Different countries use different standards. Currently, we are using this. Really doesn't matter for me for this demonstration. Okay, now I run the calculation. Right, so it has done the calculation. It is showing me three red lines here showing 3-phase short circuit here. Okay, it is telling me what is the level of fault. It's 14, almost 15 Ka is the fault current. And what does that tell? That tells me a lot of things. What should be my rating of the switch gears? Make sure it's more than that. Otherwise, if a 3-phase fault happens, something will get damaged. Okay, so that's good. We know that here, right? And someone wanted to work it out. They did it. The other one, remember we said about this line 5-1, it's 50% halfway. If there was a fault halfway between the cable, a 6.179 Ka fault will be measured if it happened. All right, so let's say, what if someone says, what is here? Okay, I want to do that. Another quick way of doing is I can right click here and I say to here, setting analysis, please don't do the calculation here. Okay, do it here, right click, setting analysis, I want it here. And then I can now, it will not do here, but it will do the fold level here. Remember, the fold level here is 14, almost 15K. Here should be more than here, because as you go down from the source, away from the source, you should get actually increased, what do you call it? Fold level. So now, actually the system has created calculated the 3-phase fold level here. Okay, I can do both together actually, if you want. Doesn't mean you can't do another one. I can do both together and go okay, and you can see both and compare them. So this is both here. This two is actually on the node, not on the cable. Now, it sounds strange why here the fold level is high, okay, and here it's low. Okay, well, it could be because of this generator running here. Okay, because currently you could see when we did a load flow study, the current is coming from here. Okay, and that's basically the calculation. But generally you'll notice that if there is no generator running here, you could probably see if the further you go, the fold levels should decrease, the fold currents. Okay. Now, this is pretty much sort of load flow and studies I wanted to show you. Next thing I want to show you is hosting capacity. What does hosting mean? Now, sorry, before I go there, I just wanted to show one more thing. In this one, which I opened, see the same answer is shown here because they are the same project. Okay, it's the same project. The answer shown in the bus bar here is also that. So that's why I'm saying this is connected and they are the same project. Okay, so I can close this now, this one. Next is going to hosting. Now, what does hosting mean? Hosting is, these days, a lot of people are putting PV solar panels at their homes and farms or whatever. And here's a simple network shown here. Okay, and what it's you can see the line drawn here, and it's showing different voltage. I can show this in two ways. If I right click here, let me say I right click on this line and say show me in the schematic format, because you might say what is this? And this is actually the whole network. Okay, that's the network of this, which is drawn in the geographical layout. So sometimes it's very not easy to understand in geographically, because people understand like schematic single line diagram type thing. Okay, now the beauty is when I was here and I clicked here in this line here, that's yellow, and in here it should be, one should be yellow here, up here, sorry, line 18. Okay, so now you can see when I came here, I know exactly where in the schematic. With this is quite a complicated schematic, right? How do I find it? So it puts a yellow color here to show you, and that's this one. And if I double click this one, you say show parameters, you can see it's line 18. Okay, so that's the same line. Another thing I can do is I can actually bring this diagram and put it here in this on the side, and I can expand this, and so it's like in the same one I've got picture in picture. Okay, I have the single line of the schematic of the calculation. But today we'll close this. We'll just look here in the schematic. So what is hosting study which Neplan offers? people want to connect and they go to the utility and they do application, they want to do certain thing. It takes ages for them to work it out. Can they connect a PV cell? Or can they connect a EV charger at that point? How do you know whether there's enough capacity or let's say enough power left for you to put a charger there? A charger could be easily 50 kilowatts, could be 150 kilowatts, can be a 300 kilowatts. So you just can't put it anywhere on the network because you need power, right? So what Neplan has done, they've created a module called hosting capacity, and you can go here, and I say I'm going to do e-mobility, which is that, and I want to know what is the power at that connection point. Okay, so now I'll go okay, and I say calculate. So the system is now going around and calculating it. Right, so now I can go and zoom in and start seeing if I can see any results. Yeah, I can see some results. So I can see here, that size here, I can connect 32 kilowatt EV charger. Okay, over here, I can put 60 kilowatt charger. Okay, and all other points are also there. Same over here, what can I put? Okay, at this LV network, I can put 91 kilowatt. And over here, 65. So, and different location, different amount of power is available to put. So based on this, you can quickly make a decision, okay? So quickly. What else can we do? What about things like connecting a wind, renewable energy, wind or whatever? What can I do? Where can I push power into the grid or even PV cell? So I will change my setting here. So, and then do the same. And now you can notice here, at this point here, that's 48 basically is the size of the the EV charger I can put. But now I'm going to say how much energy can I generate here. So let me do the calculation. And now the calculation, please. Please remember the calculation is not happening in my machine. It's happening on the cloud. Okay. So here I can push 87 kilowatt of power. If I put a PV cell, I can do that. So this is something I wanted to quickly show you how much what we can do with our hosting study. Very useful tool. All right. Next is ArcFlash. ArcFlash study is also a very important thing that's going around in the world. Everywhere people are requesting for ArcFlash studies. Why? Because it's important to protect the people. Okay. If you put a switchboard, obviously, if there is some sort of short circuit happens, it will have a flash, big arc flash, and then if people are not wearing the right uniform, like PPE, you call it, then they can, they'll burn and they can die even. They can get severe burns. So in this case, we are doing a study. So to do arc flash study, we still have to do short circuit study, but in the parameter setting, I have to go into this and I have to tick this button here. Can you see it says arc flash calculation? And then you can choose any of the standards out of these to do the calculation. Okay. So we will use NFPA, which is National Fire Protection Association one. So it doesn't matter. In fact, you can use anyone. They all give, little bit answers like that. Choose your, you want any inches if you are coming from Imperial, reading areas or metrics people, so choose it and then go okay. And you have to put also all this clearance time and all this information from your system. Okay. Now, once you do that, you are ready to do basically calculate. Okay. So do the calculation. Now the system is going to calculate. All right, so now it is giving me an answer here, pretty much telling me that this bus bar in yellow, I mean, obviously we have a short circuit here. Okay, we have created a short circuit here so that this particular switchboard will have a arc flash, and it gives me the energy levels it's going to generate. Okay, so the ITPV and EB, I think ITPV stands for arc thermal performance value, and ETB is energy break open threshold. So these are the ratings that are people looking for designing the uniforms. Okay, what should they be wearing, and also this is giving us what is the energy level at 460 mm away from this bus bar. Okay, you know, if you go here in the table, it will give you more information. As you go away, of course, from different bus bars, you're given all of them, and it tells me how the energy will drop as we go away. For example, in this case, see, the energy is so much, but as you're going away, the numbers are falling, and that makes sense. Okay, so you can produce, export this, and give this as a report to your client, let's say, okay, and say this is what you have to do, and they'll make the necessary, you know, arrangements. So that's simply a very quick one here. The next one I would like to touch base here is example on a photovoltaic calculation. So in this case here, I think this example was shown on the PowerPoint slide. Here's a utility network. Of course, there's a transformer here, 20 kilovolt. Okay, and then you got 1, 2, 3, 4, 5 bus bars in this case. Okay. Now, these are inverters here. Okay, which is going to produce power. They are AC. Okay, so we don't have to worry about the DC circuit about at the moment. Okay, we all worried about the inverter. So if you're giving the inverter model here, you can use this and inject it into the grid. Okay, and if I did my calculation, so now the data has come up here. Okay, and pretty much what it is telling me is, if I look from this side, you can see each of the cell, they are making about 20 kilowatts each. This one we're doing 43, sorry. And therefore, it's traveling across through the bus bar, through the cable here, and out here, and then stepped up and goes through to the grid. That's what grid is importing, right? If I want to turn off one of them, I can just simply click here. And this inverter is now off, let's say, and do the calculation. It should, the power IT should get, you know, reduced to half. So whatever I'm producing is now 38.66 kilowatt, okay, because this is off now, and this is only producing power. So why 38? Because obviously there's some losses on the way back to here, okay. Yeah, so that's pretty much it that I wanted to show. Pooja, you there? Hello?
Yes, Bob. Yeah, I'm here. I'm here.
Okay, okay. All right, that's it. I think I've just ran out a little bit more than normal time, but I guess that's all right. If you have any questions or anything, then we can answer.
I've
Otherwise,
put it in the chat box. There have no questions come up.
oh, no
Guys,
question.
it's a good opportunity. If you really have questions, you want to ask something, it's a very nice opportunity. Please ask questions. Do not hesitate. Put it in the chat box. I'll bring that up. I'll give you 2 minutes to do that. Bobby will just wait for 2 minutes. If someone has any queries, it comes up.
No problem. Yep, that's fine.
Okay, just 2 minutes. So no questions, anybody? It seems we don't have any questions. I've
No.
shared the feedback link in the chat box. Please fill up the feedback link and the certificate would be provided to you.
Okay. Thank you, everyone.
Thank you so much, Madhuri. Thank you so much, Durgeshan sir, for being here with us. We'll see you on next Thursday with
All right.
another new software.
Thank you,
Okay.
Thank
Thank you
you
teachers.
so
then.
much.
Thanks. Bye-bye.
Thank you, students, for attending. Bye-bye.
Bye.
Bye.